Hey everyone, Mr. Canistero here. In today's video, we're going to talk about one of the funnest topics I know about, and that is friction. So, I'd like you to start off. We're going to perform a little experiment ourselves. Right, you can do this right at home, and we're going to think about what are the factors that affect friction. So, do the following. Wherever you're sitting, find a flat area and take any old object, whether it's book, phone, etc., and place it down there. What I'd like you to do is simply pull on the object and feel how much force or how much you have to pull on it in order to get it to move. Okay? So consider that for a second. Once you've pulled it, we're going to change a few things. If you can, find any other surface, whether it's paper, whatever, and put it on a different surface, something that's maybe a little bit rougher or something that's a little smoother. Pull the object again and see if that force is any different, more, less, the same, etc. Okay? If it's rougher, you should be feeling one thing. If it's a smoother surface you're pulling on, it should be another thing. For the final experiment, do the following. In addition to pulling on it, I'd like you to push down on the object as well. Now what you want to examine is, how does the force to pull it to the right or to the left change as you're pushing down on the object? And for everybody, I'll pause for a second so you think about it. So for everybody though, if you're pushing down on it, you see that it's a lot tougher to get it moving. So what are we changing when we're pushing down the object and when we're changing the surfaces? Well, in the first experiment, we simply, by changing the surface, by going from a smooth to rough surface, we change the materials. Okay? So something about the two materials has to do with how easy or hard it is to get it moving, which is kind of going to be the essence of friction. The other thing was, we saw that by pushing down on the object, that also made it tougher to pull. So think about this. When you push down on an object, you know that that surface has to push up against you. And one of the things we learned about is that force that the surface has to exert up against you, that's the normal force. And so by pushing down on it, we're really affecting or altering the normal force. And so when we think about friction, when we're talking about how easy or tough it is to move an object across the surface or drag an object, really it depends on two things. The two materials that are being rubbed up against one another, and it's going to have to do with the normal force. So let's go ahead and jump to the more formal notes. Before we do that though, and I would like you to consider one last example. Consider a tire rubbing up against the road. Now most tires are fairly smooth, but if you were to look at this at the microscopic level, what you'd see is the following. The tire looks like a rigid object, a lot of bumps and ridges, etc. And the road also looks like a bumpy, rigid object as well. And so when the tire is trying to go over the road, all those little bumps and ridges kind of get caught in each other, and it's really tough for the tire to go over the road because all the little bumps and ridges really getting caught. Friction at the atomic or microscopic level is the sum of all those little forces that are occurring, where the two sides, for example, right here, the two little jaggedy pieces are pushing up against each other. If you add all those up together, you see those add up to the force of friction. At the atomic level, what's happening here is it's all the electrostatic or electromagnetic repulsion that's occurring between molecules. So really, friction is an electromagnetic effect. It has to do with electrons repelling other electrons as they're getting near each other. So as we talked about just a minute ago, we saw friction has to do with two things, the materials and the normal force. So without further ado, the equation for friction force, we say the friction force, I use the F for the subscript F, equals the Greek letter mu times the normal force. Now mu is called the coefficient of friction, and it simply refers to what are the two materials you're talking about. Finally, before we jump down and talk about mu some more, oftentimes I'll call the force of friction, I'll just use the letter F, make it kind of curvy. Mu, coefficient of friction I always keep as U, and then normal force we'll often use is just the capital letter N, which is why friction is really the funnest equation we're going to learn. So let's talk about mu a little bit more. Mu can be two things. It can be a static or a kinetic value. So if you ever think about trying to move a desk or a table, you know that it's really, or even a big rock really, it's really tough to get it started. But then afterwards, after you get it moving, it's a lot easier. So at the microscopic or atomic level, what's happening? Well, when that tire is going over the road, if it's standing still, it has time for all those little bumps and cracks to kind of sink into the road and kind of get lodged in there. When they're lodged in there like that, it's very, very tough to get it dislodged. So when an object is standing still, we're going to call that static friction. But once you've gotten that tire moving and it's already over the road, those little bumps, it's a lot easier for them to glide across because they're not going to fall down into the cracks as much. And so we're going to see that there's another type of friction called kinetic friction, and that's when an object is already in motion. So here is just a quick little table showing you tons and tons of friction coefficients, all the different ones. We're going to use the letter mu with a subscript s to represent static or standing still friction, and we're going to use mu with a subscript k to represent kinetic or moving friction. And for every example, whether it's steel on steel, or you can see something like glass on glass, or even things like, let's go down here, ice on ice. You can see that all these friction values have all variety of ranges, but in all the cases, the static friction is always greater than the kinetic friction. So right from the table, that becomes apparent. You also see things like how wet materials have lower coefficients than dry materials. So, or for example, how a lubricated material has a lower coefficient than a non-lubricated material. That's also explainable by this kind of crack, or not crack, but like the peaks and troughs model we've made. If we imagine, for example, a pan or the ice, whenever there's water or a lubricant on it, it's like you're filling up all those little cracks with stuff. So for a saute pan, for example, you're putting oil on it so it doesn't stick, so there's less friction. You're filling up all those little tiny bumps and cracks in the pan, so that when the food or the stuff gets on there, it can slide across it because the cracks are filled. Finally, one last thing to note before we slide down. Friction always resists the motion. That means no matter which direction you're pushing an object, even, for example, if you have a box sliding down an inclined plane, we know the friction force is going to oppose it. It's going to be in the exact opposite direction. Or, in an alternate example, if you have a box that you're pushing up an inclined plane, so here's a person pushing on a box up an inclined plane, the friction force would actually work against the person because it's always going to go in the exact opposite direction of how you're moving. So, finally, we're going to ask, what are the units of the coefficient of friction? What do we know? What do we measure that coefficient of friction in? Well, what do we know? We know that the friction force is the coefficient times the normal force. So if we want to solve for the coefficient of friction, we just divide over. And so dividing over, I get the following. The coefficient of friction is the ratio of the friction force to the normal force. We know friction's a force, so it's measured in newtons. And we also know that the normal force is a force, so it's measured in newtons. And so dividing newtons by newtons, we see that they cancel out. And we get no units. So what does that mean? The coefficient of friction really has no units. There's nothing we measure it in like meters, kilograms, seconds, etc. Because it's a ratio. It's just simply a number like half, pi, 73, etc. It just tells you what is the ratio of the friction force to whatever is pushing down on it. Finally, what if you're pulling an object at a constant speed? What's the force of friction then? Well, if an object is being pulled at a constant speed, so velocity equals constant, we know from before that means one thing and one thing only. It means the acceleration is 0 if it's moving at a constant speed. If its acceleration is 0, the net force is 0, so the object is in equilibrium. One of the most important words in all of physics. So whenever an object's being pulled at a constant speed, it must be being pulled with some force, which we're going to call force applied. You have to be pulling on it if it's moving. But because it's moving, and it's over these rough surfaces, we know there's a force of friction acting on it. Now, equilibrium means all the forces cancel out. So whenever an object is moving at a constant speed, the force of friction must be equal to the force applied, or all the forces acting in the opposite direction, because the force of friction is going to act to cancel out the forces in the opposite direction. Then the last thing we'll talk about, what does a typical graph of force versus time look like when you're attempting to move an object? So envision the following. You're trying to pull a table across the room. So you start off, you're not sure how hard to pull it, so you pull kind of very lightly. And then you slowly increase your force because you're really not sure how hard to pull it. Eventually, you reach some point right here when the table starts to move. Then immediately after that, it becomes significantly easier to move, and so you don't have to apply as much force, and really you don't pull as hard. And then finally, after the table starts to move, you notice it finally begins to taper off, and the table moves at a constant speed. So why does the graph look like this? Well, for two reasons. Where I started, that's where you've overcome the static coefficient of friction. When the object is moving at a constant speed, it's because the kinetic coefficient of friction is a different value, and your pull is balanced out with the kinetic friction. So really all in all, though, if we want to sum it up on one thing, you should really be thinking about friction as the following. Simply using the force of friction equation to solve problems, understanding that F, the subscript F, this is force of friction, mu, that's the material part, the two surfaces you should be thinking about, and Fn, that's the normal force. How hard are you pushing down on it? Now, typically, that's just the weight of an object when it's on a flat surface, but it could be different if you are physically pushing down on something, like we did in our opening thought question. So, lots more to come. I hope this was a nice introduction to the topic. Have a great day, everybody.